Well, a very good afternoon, good evening, good morning, depending on where in the world you are tuning in from. My name is Adrian Reed at Blackmetric, and I'm really pleased. We've got a really interesting speaker and a really interesting topic for this BA community webinar. Our speaker tonight is Wim Debreuck, who is going to be talking about systems dynamics, the BA tool you didn't know you needed. Now, if you're aware of, if you've studied systems thinking, you'll know that systems dynamics is a real core set of techniques within the world of systems thinking, and it's really quite an interesting one for us as business analysts as well. So before we get started, just a little bit about Wim. Wim's mission is to explore strange new behavior, to seek out new specifications and new business value, to boldly design new systems where it matters. I first met Wim at a conference, the BA and Beyond conference over in Belgium, where I was really enthralled and interested in his presentation and how he talked about the projects that he had worked on. So I'm sure that all of us are going to find this very interesting this evening. Also, please do ask questions. So you'll notice you have a Q&A, a question function. We'll be taking questions towards the end of the webinar, but feel free to type them in whenever they occur, and we'll cover as many of those questions as we can at the end of the session. So now, with a presentation entitled Systems Dynamics, the BA tool you didn't know you needed, Wim, over to you.
Okay, thank you, Adrian, and welcome everyone to this presentation. Thanks, Adrian, for the nice introduction. So let's kick off. So as a good business analyst, I would like to kick off with the question why we are doing this presentation. So that's also always a good question. Why are we spending time on this? And let me tell you a story to set your mind about Mr. Patient. So Mr. Patient, imagine someone that has a life-threatening disease, and he needs to be treated, and he talks to his doctor, and the doctor says, okay, Mr. Patient, it's a difficult problem. You are in a bad situation, so we need to do some investigations. We have to do some elicitations of your problems. We have to capture some data by doing some exams and investigations. We need to do some scans. And okay, the doc tries to come up with a solution, and he evaluates some options, and he talks about with colleagues about how to tackle this particular Mr. Patient. And he comes back to the patient and says, okay, I have worked on it. I have processed all the data. I have evaluated all the options, and I architected a solution. I'm very fond of it. It's extremely never been done before. It's going to be awesome, and we are going to give you a cocktail medicine. We're going to do some operations and so on. And okay. And Mr. Patient says, okay, that's good news, I think. So how do you think this cocktail and this treatment, how is going to affect me? Huh? How I'm going to react to this? And the doc says, I haven't the faintest idea, Mr. Patient. I don't know. It's never been built or treated before. So I don't know if you see, if you saw some similarities between the activities that the doc executed and the activities that we do as a business analyst. We try to explore the domain, we investigate behavior, we come up with a solution, we evaluate the options, and then let's face it, we push the button, execute the the solution, and we haven't the faintest idea how it's going to react in real business life. We don't know. We trust it. We have a good feeling about it. We are very enthusiastic that we can do it, but actually we don't have any data that supports the successful rollout of the solution. And that's why I tried to look for a solution how to tackle that. And I came up with, I was thinking about behavior and what actually is behavior, and you could look at behavior as a combination of functions in time. And that's what this presentation is going to cover. I hope you see at the end of the presentation why a study of behavior is important in every project, and I hope you catch something extra as a tool to do the job as a business analyst even better. So let's go. So about me, Adrian covered the most of it. So I've been designing systems for more than 10 years now. But what I want to add is the data science part. So I'm one of those believers that thinks that a business analyst should also be a data scientist at certainly at some kind of level, not an expert level, but at least the junior level, that you could explore also the data that's already out there. It's as important as doing workshop, exploring the stakeholders, and so on. The data is also a very important entity to explore. So behavior is defined as a combination of functions in time. So let's try to erase the mindset, and let's try to look at a process in a little bit different way. So if we look at behavior, it's something that we, as a business analyst, we study the current behavior. We need to do that because if we don't, we can't get those requirements out, and that's what it's all about. So we study requirements, and then we come up with business use cases, product use cases, whatever you call it, whatever methodology you use, but you define some stuff that needs to drive a new desired behavior. You need to accelerate or to add business value. How can you add business value? By changing behavior, behavioral systems, behavior of persons, whatever. So those business use cases are going to drive that new kind of desired behavior. So, and it's an intuitive approach, of course. So it goes on and on. So if we say, okay, this is actually something that we do, we could say, okay, why don't we study those functions also in time? So that's at the core. Yeah? So, but what do I mean actually with functions in time? So let's take a step back, and actually, functions in time is nothing else that stuff happens. Stuff happens in real life. And if you think about it, there are only two things of stuff that can happen in real life. At the one hand, I call it the expressible stuff. Things that happen that you can express with a formula. It's mostly machine or physics related. It's very expressible. So these are things like okay, the heating, the production per hour. we have some delays, exponential delays, for example. We have vaporization if we know the kind of liquid and the square meters and the temperature curve. We can express the vaporization flow in time. We have dependency expressions, so you catch my drift. So that's expressible. That's the easy part. On the other side, we have the non-expressible stuff. That's what we actually don't like. It's more, it just happens. It's you can see it as a stream of events. It's mostly not. It's mostly human related. So examples for you could say customer orders. We don't know actually when a customer is going to push the button. An employee starts working. If you work with IT people, you never know when they are going to come in. It starts raining. Okay, you could say we have weather forecasts, okay, but they could be wrong. So that's not really machine. That's not really human related. But we could have a machine breakdown. It's pretty unpredictable. All kinds of human interaction. Marriage, for example, is many people apparently that are listening going to agree with me that marriage is pretty unpredictable. A bad gin tonic, it could happen to you, so whatever. So that's the non-expressible stuff. So the left part, the expressible stuff, as a business analyst, those are the things that we really like. So that we can put a formula on it. We have some semantics for it. It's something we love. It's in our habitat. So the other stuff, the non-expressible, the ad hoc stuff, we don't like. We call it chaos. We abstract it. We can't really do anything about it. It's very difficult to explore. So we don't really like it. And what we tend to do is translate the non-expressible stuff in averages. We really like averages. So we're going to, for example, express the customer orders. We're going to say, okay, we looked at history and we have a customer order rate of, I don't know, 10 orders per hour, something like that. So we take the non-expressible and we express it in an average. That's something we do all the time. And that's of course where it starts to go wrong, because even more and more in the new age, we can't rely on history to make statistics and to make averages in a world that is increased by very rapidly business changes. The history as a value is dropping. Okay. So functions in time, of course, we need the reality. So we need, of course, the data. The reality is expressed in data, so we need the data, but the data today is not really a problem. We have data all around us. We have existing relational databases, ERP systems with billions of records. We have new NoSQL databases. We have IoTs. We have API, public API services, whatever. Data cannot be the problem today. It's very cheap. It's compared to the old days. It's everywhere. It's cheap. If it's not there, it's cheap to create it. You can place a sensor, whatever, to capture that real stream of events. Instead of using an average, a statistical average, you can use real data to feed to those functions. and then that's where system dynamics comes in. It's a modeling technique. I'll come back in a few slides later, but for now it's a modeling technique that can express in a fairly easy way those functions in time. And the fun stuff is that you can use the model not only to simulate reality and to predict and to see what is going to happen, but you can also use the model in real life as it presents to you. And so think about weather forecasting, and the weather forecasting is using constantly the reality, the new data to adapt its prediction. So the weather forecast for next week Monday will be much better tomorrow than it is today, because it's going to process the reality or the real weather of today. So, and if you run it, and that's pretty cool. If you run it, you can actually verify if your system, if your newly designed system is really answering to that desired behavior that you try to design. Something that we let's face it, that we rarely do. As an external business analyst, it's mostly you're not in the room anymore when that happens. And so you design, you architect, and you walk away. So system dynamics, if you want a definition, that's just a Wikipedia one, but it was actually invented in the early years 50. From an engineering point of view, even before software and IT was really in place, but it was used to model complex operational processes, and it was also then used by a couple of very smart people, the Club of Rome. If you just Google them. You have system dynamics also used in a kind of social cultural way to investigate water shortage, for example. There's also a model called World Tree. World Tree is actually the predicament of mankind when it's going to stop. Just Google it, but it's pretty interesting, because if we would have had World Tree model running, perhaps we could proven that climate change is actually there. So much sooner. Let's hit the ground. So that's a little bit of introduction. Now I want to convince you the power of system dynamics modeling. So let's use a very simple example. So here we see a BPMN process with just a two-step process. So if you look at the middle swim lane, you have an approval request, and then there's one department or one entity that needs to approve the first step. So it's the first approval process. It's okay or it's not okay. If it's okay, you have a second approval process that looks at the request and then evaluates if it's okay or not. And at the end, the process in its whole form is approved or not. So it's a pretty hello world process BPMN design, very simple. So if you would model, and don't be scared, so don't get backed off by this model. So this is the system dynamics model for that two approval process. So you will see some recognizable entity. So the difference between a BPMN approach and a system dynamics model approach is here we take the whole bunch of processes in reality. So here we are going to see things as, so there are a number of requests coming in. We have a certain request rate that is piling up in processes or approvals that need to be approved. It comes to the desk, imagine a manual approval process. Requests are piling up at approval 1 desk. They get rejected or they get approved. We have a average percentage of approval. We have, you see those averages, and so we really like those averages. So at this point, we are only able to use averages. But we have, for example, the average time that it takes to approve in step 1. We have the average time that it takes to approve in step 2. We have the number of approvers at the first stage. We have the number of approvers at the second stage, and so on. So here we see a kind of multi-cause diagram. So you have, even in such a small model, you have some dependencies. We're not going to go into detail, but what you can do with this kind of model is also some questions, and now it's getting interesting. We can answer some business questions. So given a set of values, for example, we have a request rate of 2 requests coming in per minute. We have an average time of evaluation in the first step of 2 minutes, in the second step of 6 minutes. We have an approval rate in the first step of 70%, and we have 55% in the second step. And business asks us, as a business analyst, okay, tell me what's the minimum staffing on department of approval 1 and on department approval 2? What's the minimum number of FTEs that I need to make that work? So we can run that model. I'm going to talk about the tool after the model in a little while, but we can run that model and ask for some data. If we run the model and we say, okay, let's try this with one guy or one person at approval 1 desk and one person at approval 2 desk, we see we're not actually going to make it with those two people. In the left upper corner, we see a graph, and that's the number of requests that are piling up at approval 1 desk. So we have 1 day time, so we have 480 minutes, and we see that we have about 700 requests laying at the desk at the end of the day. So that's not really a workable scenario, because the day after you're going to start with 700 and the day after with 1,400. So it's piling up. It's not an operational solution to do it that way. Same thing for the approval 2 desk, the right upper graph. We see that we have almost 200 requests that are piling up. At the end, at the bottom graph is actually the result. So we have about 80 requests that are actually are getting approved at the end of the day. That's the production result of that scenario. 1 at approval 1 desk and 1 at approval 2 desk. So let's try it with 3 people, for example. We see that the pile at the approval 1 desk is a little bit better, but yes, it doesn't impact the total result. We are still facing an 80 number of approved requests. So the adding 2 FTEs on that department is just a waste of money. It doesn't change anything, and you have still the problem that your piling up stuff that you can't process the next day. So let's try 3 people, for example. Oh, that's interesting. So we see kind of oscillation behavior, and we see a kind of flat line appearing at first between 2 and 6, and then between 6 and 8 number of requests that are laying at desk 1. That's already viable. That's doable, because the day after we're only going to have a maximum of 8 requests laying around. So we have a throughput in approval 1. So we see that the result is still not impacted, because we have still the 80 result figure, and we have still the approver 2 piling up into a bunch of requests that are not processed. So 3 is better but it's not solving the problem. So just to try a situation at 5, so we increase it, and then we see an oscillation that is a little bit better. So the next day we could go to the office and see only 2 requests laying around, but it's not significant. It's not significant any better, and it's certainly not worthwhile to put an extra FTE on that department. If we go back to 4, and this is the 4 scenario with 1, this is the 5 scenario still with 1, and then we add another at approval 2, and we see that there's still no real there's still a bottleneck at approval 2, but we see a much better throughput of the requests being approved, and we are now at a number 150. So that's better, but it's still not a solution. It's as of 3 people and approval 2 that we see the same or similar oscillation behavior and a kind of flat line, that we have a stable number of requests that are in the queue of approval 2. So this is actually the answer to the business question. The minimal staffing to have a workable 2-step approval process, given the numbers that we defined in a couple of slides ago, given 2 requests per minute and so on and so on, the minimal staffing is 4 people at approval 1 and 3 people at approval 2. And then we get a throughput of, let's say, 400 or something requests at the end of the day. So that's the answer. So you can do things like that with system dynamics modeling, even in a very simple way, and you can simulate behavior given a number of parameters, and you can optimize whatever you want. So this is just touching the top of the possibilities. I'm just going through a very example that we did at Bridgestone in Belgium, and I'm just going to tell you very fast, because we need to leave some time for questions, of course. But the story is interesting in that way. We designed a transporter system for bringing containers from harbor to the first warehouse and back for Bridgestone, and it's a very specific planning engine. And to make a long story short, so we deployed it. It's a very big project, and we deployed it, and we tested it in advance and so on. And then the first day everything went very well. Everyone was very happy. It was a very successful launch. And then the second day, third day, no problem. But at the end of the week, we got a problem that we had very big waiting times for drivers coming up on the yard of Bridgestone. So we solved the problem that we had waiting lines at the harbor, but we created a new problem that we had waiting lines at the yard. And actually it was pretty disastrous because Bridgestone had to pay for the drivers because that was their problem. The yard was not free. There were no empty addresses and so on, and we needed to cancel the project. We pulled the plug and we took the system away, and we went back to square one. So that was a long story, but eventually we put a system dynamics model in there now, and it's running. And now we can detect if we it's not autonomous yet, but now we can detect when we're going to have problems on the yard if we don't change anything. So now we can see in 10 days we're going to run out of empty yard addresses. So we can solve that, but by diminishing the number of drivers that are bringing containers. So that's answering the business in a different kind of way. So this is a little bit the process. I don't want to spend too much time on that. But the business goals in that project were, for example, the warehouse staff must not get out of work. We need to avoid empty driving. That's specific. But the free yard addresses should be available, because no free yard addresses means you can't drop a container, and so on. So the system dynamics model that we built looked like this. And you have, in system dynamics, you have positive feedback loops. It's all about feedback. It's about, in the systems thinking context, of course, that everything is influencing everything, and you can design it so that you actually see how it's working. And that's pretty powerful. And under the hood, it's nothing else than pure mathematics. It's you probably remember the integral functions of your math schools. So you have an integral 0 to t, then a function, and those square boxes are actually each time an integral function that is expressed. So, but you don't have to do that. The tool is helping you. You just have to design the multicast diagram and then put some expressions on it. To close or to wrap up, you could say system dynamics. It's a very old methodology or modeling technique. So why do we need it now? And we didn't need it before. So my experience is why should you use it, or why could you use it? Because the new systems are getting more and more wicked. I saw a presentation of some guy, and it was a really interesting story about wicked problems, but it's not for this presentation. But the systems today are, let's say, need to be smarter and smarter, of course. And so, and to be smart, you need to incorporate as much of the real life as possible. So. It's just the way it is. So you can use it today because data is everywhere, and it used to be very difficult to capture data, but now it isn't anymore. So that's no excuse. There's data even before the new system is in place. You can design a model and run the behavior before a new system is designed, and see how current behavior is reacting to changes in reality. Even that exercise is for business a real eye-opener, because it's something that you can't do in Excel. So it's you can, that's then next level system dynamics, but if you going to that space, you're really going to get blown away. You can replace your averages by real life data streams. So in the example of the approval process, we took an average of 2 customer orders per minute. But imagine if you would plug that into the real request rate, the current request rate, then you would have a model that is answering business okay, and not given the certain theoretical input. You would answer the business. So okay, given the situation that we have today, we see that we are going to need 1 extra approver on approver 2 to have the most efficient throughput, or we need some people. We have some people not doing anything efficient now. So let's let them do something else. So a little bit of advice: start simple, enjoy the process. It's really fun to do the modeling itself. And it's not, and certainly not at first hand, it's not about getting the thing 100% correct. If you start out, you will see that there's a lot of value in the process as such. Just as you design processes, you never hit the 100% correctness at the first shot. And it's an iterative work. It's a work in progress, and it's a little bit of the hard versus soft systems thinking. I learned a lot of Russell Ackoff and Mr. Garidacci. They're not into system dynamics. They're more into systems thinking, but they have some interesting literature. And if you Google, if you really want to get hands-on, and that's my let's say, that's why I'm so enthusiastic about it, that it's not just a theory, but you can really use it in real life projects and problems. If you Google Professor Erik Preut, it's a professor from the University of Delft in Holland that did some magnificent work on system dynamics and has an excellent online course. The tool that I use is Vensum. There are a couple of tools to do system dynamics, not that much, but Vensum is even the previous version. There's new version Ventity, I believe, but I'm hooked on the Vensum tool, so it does what it needs to do for me. And if you want to know more on the subject, just check my LinkedIn. I publish the presentations, and perhaps you can drop me a message if you want to know more. So I thank you for your attention and for joining us. So back to you, Adrian.
Well, thank you very much, Wim, for a really interesting, broad look at systems dynamics. I can see we have a number of questions coming in. We'll cover as many as we can. And as a reminder, if you would like to ask a question, please just type it into the Q&A box. So Wim, we've got 2 similar questions that have come in around software tools for modeling systems dynamics. And I know you answered that to some extent, but do you know which customer or website, if someone was interested in getting hold of that piece of software, do you know who the publisher is, Wim, that they should contact?
I actually think that the company is called Vensum.
Okay.
But it's if you Google Vensum, let me see, it's Vensum.com, that's the one, yeah. Vensum.com is the website when you can find those tools. You have a free version, but you have also an enterprise version, but it's not, the license is not that costly, so.
Yeah, definitely. Okay, fantastic. And then we've got a question about the difference between expressible and ad hoc, which was something you started in the beginning of your presentation, Wim. And,
Yeah.
and the question is, the ad hoc, is that what we as BAs call exceptions?
That's an interesting question. Perhaps sometimes it is. Exceptions, we don't like exceptions, of course. It's something that is messing things up. But I would not call it exceptions. It's just, if you think about it, it's just the stuff that you don't have under control, and the world is full of it. And we in a process design, we mostly are let's say, not incorporating the ad hoc stuff.
Yeah.
So the machine breakdown, for example, if you're let's say you're building a system and you need to predict when the next maintenance job is need to be executed on machinery. You will have a couple of parameters, running number of hours on the machine, and then when the maintenance needs to be executed, but you don't have machine breakdowns. And if you incorporate it, you will incorporate it like as an average, and that's that's good. It's better than no average, but much better is replacing the average by the actual number of breakdowns.
Yeah, it's really interesting, because I'm just thinking the question through. It's probably one we could talk through for quite some time, and because I'm wondering whether even the term exceptions in the BA world is quite broad, in that you sort of have planned exceptions, exceptions you're going to get, but then there will be almost having to cater for completely unknown and sometimes unknowable events. So maybe it's about variety of demand and elements of uncertainty. Would that sound right, Wim?
Yeah, you always have an idea of how the behavior is going to be, but of course that's why we have a whole bunch of maintenance people sitting in departments tuning the system when things change. So you have people pushing buttons at the end of the month because they know that financial guys are closing, and you have whatever. Do you know the? Well, I don't have the picture with me, but Amazon Go opened a retail store, and their new stores in Seattle, and they published it as no queues, no waiting lines, and then you see a picture with a bunch of people standing in line.
Yeah.
So so something was wrong in the design. That's obvious. So if you don't have to look that far, if we design cities and traffic flows, well, yeah, we have bottlenecks.
Yeah, that leads us on to another question, actually, Wim, which is about SD and learning. And I mean, the question is do SD models learn? But I think probably what the person means by this is that, can we use SD modeling to almost have a hypothesis to experiment, and we then adapt it and we learn more? So can the organization learn about the situation through SD models?
Yeah, sure. It's once you start with it, it's really an eye opener, and you see if you do it wrong, you will see strange behavior. So it doesn't add up. So then you start to think about. So we're running the model, and I don't know. You get a number of thousands, and you actually expect 10. Right? So obvious your model is wrong. That's pretty obvious, or else you would get a number around 10. So, but now you're getting thousands. So what's the problem? And then you start to think what I'm missing. There's some parameter, there's some influence that is not in the model. So and the process in doing that is so valuable that you learn a lot of the current situation, but also the situation to be, and perhaps you make a conclusion that a very important influencer is not an part of the system, and then it's going to be it's going to not work out. So.
Definitely. So you've got that kind of diagnostic approach as well, potentially isolating areas of the system as well. So,
Yeah.
Okay. So the next question is, can you use SD without BPMN? Because I know that you used you showed a BPMN model. So SD on its own.
Yeah, of course. I used it in this example more as an approach to show you what's the representation of an SD model compared to a BPMN model. But even in mine projects, I don't BPMN everything, and it's not a dependency, certainly not, and it's even worthwhile to, for example, in a workshop, you don't have to explain everything and the core of SD modeling, but just do a multi-cause diagram workshop and translate that in an SD model, because an SD model is nothing else but a multi-cause diagram, and you can use that the output of that workshop as an input for your model, and then get more detail in there, and then eventually run it and simulate it. It's certainly not a dependency to have the BPMN model in place. No, certainly not.
Definitely. Okay, so our next question is a bit of a tricky question, Wim. So I'm glad it's you answering this one and not me. So it's, what's the difference? Because you mentioned hard and soft systems. How would you describe the difference between hard and soft systems approaches?
Well, hard system approaches is originated more in the engineering context, and so more the goal to have some solid 100% solution model, and that's the goal. So if I need to come up with an example, a hard systems thinking approach would be in some factory context, that you have real dependency on what machines are depending on what, and the number of energy that is consumed, and everything is fairly expressible. On the other hand, for example, a soft systems thinking approach is that World Tree model. We know that the World Tree model is not correct. Of course, it's very difficult to predict the predicament of mankind. We know it's impossible. But that's not really a problem. So soft system thinking is it's not a requirement that it needs to be 100% correct. It's more the approach of let's think about it. Let's start that process, and let's feel what is dependent on what, and in what kind of level.
Yeah, it's really interesting. I'm smiling as I hear you explain that, one, because it's just triggering a thought pattern in my head about one of the challenges with these types of approaches is boundary critique, and working out where to draw the boundary, and what is essentially a subsystem of a suprasystem or an ecosystem. So a question that's just sprung to my mind as you're speaking there is, how do you know when to stop, right? Because you could build a model that says, well, actually, we're an insurance company, so we need to incorporate weather patterns, because weather patterns affect our the type of claims we're going to get. But then other than weather, we also have to have climate change and climate, and that's an even bigger thing to model. You could end up modeling and modeling forever. When do you stop?
Yeah. That's true. Yeah, it's an interesting question. I don't really have a fixed answer to that. It's a kind of feeling. It's like, just like you're scoping your solution, you need to feel when you're okay, and it's again translating to averages. If you don't want to go there and not further model it, then you can block it with okay, let's make that an average and block it from here on. And so in your example, we don't going to model climate change, but say we're going to set an average of 1 degree increase in temperature each year, or each 5 years.
Yeah, absolutely. Good. So we've probably got time for probably one question before we conclude. So final question. Is there anything, I love this question, is there anything SD can't model? Wow.
Well, that's a very interesting one. Well, I don't think it's I started out with the assumption that SD modeling was not necessary for everything. That was what I was thinking. I said, okay, SD modeling is only interesting in those domains where you have some very complex interdependency. So like the Bridgestone case, for example, you have containers on ships coming in, you have delays, and you have workload on the warehouses and so on. And so you have a bunch of stuff that is interdependent, and it's so they say if you have more than 3 parameters that are influencing each other, it's almost impossible for the human brain to make a correct assumption. And my experience is that it doesn't need to be that complex. The example that I showed you, it proves it. And so it's a very simple 2-step approval process. But I'm sure if you would ask a business analyst and the business asks, okay, given those set of numbers, give me the exact minimal staffing, it would be not that easy to come up with the correct answer. Of course, you could do some simulations in Excel, and eventually you would get there, but it wouldn't be so easy like as we would do it with a model. And so my conclusion is there's no situation where you can't use it. But, well, I'm going to make one exception here. You need to have a situation where reality is a factor. What do I mean with that? If you have a, let's say, financial system for insurance that needs to calculate policy premiums, it could be that there's really not much reality involved in that, and it's just a theoretical calculation example. Mm-hmm. So system dynamics is really good at touching the boundaries from where reality hits the system.
I love
financial insurance, that's perhaps not so.
I love that expression, where the reality hits the boundaries of the system. That's a nice soundbite for us to sort of close on. So fantastic. Well, Wim, thank you so much for taking the time to to speak to us this evening. I am sure people will want to stay in touch. I know we have a link to your blog on the registration page, so people will have seen that. But if people want to stay in touch or ask further questions, how's the best way for them to contact you, Wim? Should they connect with you on LinkedIn or your blog, or?
Yeah, that's the last slide. So just drop me a mail or drop me a message via LinkedIn, whatever. So it's no problem. So I'm available for your questions, and I'm glad to help you out wherever I can.
Fantastic. Well, thanks once again, Wim. Really appreciate your insight into such a useful and practical technique or set of techniques. So fantastic. And also, all that's left for me to say now, as well as thanking Wim, is to thank everyone who dialed in to attend live. Thank you for attending. Thank you for your questions. As a reminder, this is part of our BA community webinar series. And really the idea behind this was to cover some topics that are perhaps beyond the topics that we normally associate with business analysis. So topics that are perhaps on the edge or on the fringe of business analysis that we can all potentially learn from. So within the next couple of days, you will get a link to the recording. So if you haven't managed to take notes during the session live, that's no problem. You'll get access to the recording. There'll also be just a really, really short questionnaire in there too. I'd be really grateful if you could complete the questionnaire. Let us know what you found most useful about this session, but also let us know what topics you'd like to see covered in the future. Because if there's a particular burning topic that you're really keen to see covered in a webinar, let us know and we'll do what we can to cover that. But for now, have a fantastic evening, afternoon, morning, depending on where you are in the world. Thanks once again, Wim, and hope to see you all again on a webinar soon.
You're welcome. Thanks, everyone.